Yes, good morning, guys. I see the number of you, quite a number has actually logged in, and I think we are ready to start. You're around 53. That is a good number to start with. The others will join as we move along. Okay, I hope you can hear me. So if you can hear me, you could send me a yes in the chat room, and then I'll be ready to go. Okay, according to a couple of you, you can hear me loud and clear. That is good. Then we can get started. Okay, so let's get started. We pick it up from where we stopped last time with a quick review. So we had already looked at a couple of applications using the formula I had discussed earlier, and that was to do with the shift property, but we also noticed that the so-called shift property is based or is directly associated with the concepts we had discussed earlier. And if you recall, in the previous lecture, we looked at how you could derive or determine or establish the Laplace transform of any given function, and that was based on the theorem that we had stated that if you have L and this is U, this is T minus A. We had our T. If you have a T minus A, I'm trying to make sure that my mouse is working fine, okay? So we had the T minus A, and this is G over T. We had something like this. And we said this was equal to E to the minus SA. This is E minus SA. And this was L of GT plus A. So we are trying to just associate these shift properties with this here. Okay. We discussed change of scale, and we looked at applications, and then we have this here. So if you have, this is all based on step functions, and remember, I justified why we do this and how this is applied in processes or phenomena that are associated with seasonalities. And seasonalities for farmers, you know, there are seasons. So, and those seasons could be seen as step functions given the nature that defines, or rather that defines the weather conditions of any given location or country. Then we looked at also the health sector. We cited examples of cancer-related kind of infections or diseases, and there are very many more other examples that would call for these applications. So in those we discussed and we looked at piecewise functions. Now in here, when we look at the different shifts, that is the left and the right, they are not far different from what we have here. So you can still look at change of scale, and then you come up with derivations that will be directly linked to this. Because if you look at this one here, before we even go into the derivation, this is directly associated with that one there. So here we have a certain f t minus c, which is e minus sc. C, of course, that will pick up the value here, and then LF of t. So the difference here, we have a certain GT, which GT here would be equivalent to 1. So if you have a certain GT which is equal to 1, remember now you look for a GT plus 1. If you take this direct there, now you have a GT plus 1, but this GT plus 1 is being substituted into a GT which is 1, which basically becomes nothing. That is what you're seeing here. But now this is FT of C. So this is directly associated with that. What I'm trying to say here is, though we are explicitly stating here that we are shifting, we have the left and then the right shifting properties, I'm basically trying to re-echo the fact that we have already been doing this indirectly. So we are bumping into something we already know how to go about. That's what I'm trying to, that's the message I'm passing forward. Right, so for this, quickly, you can just go through the derivations are quite direct really, because we've been playing with this. So you have a GT, which is, if GT is f of t minus c, then by definition of the Laplace, we move from 0 to that of this statement here. And then, of course, if you look at the entire definition up here, we have that it is t less than c. So if it is t, rather t less than 0, and remember here, the parameter of interest is c, this would be equivalent to moving from minus c to infinity. And of course, if you're moving from minus c to infinity, then this would be the same as moving from minus c to 0, and then you have from 0 to infinity. These things you did in calculus, you know, the rules. You discussed the fundamental theorem of calculus, and in your calculus 1 and 2, when you discussed the even and the odd functions, you went into this. Even when we discuss Fourier transforms, we'll still pick up some of this. Okay, so from that simple fact, which is highlighted right here, that is that simple fact highlighted there. Then what happens is, if you have a minus c to 0, then the question is the function defined in that kind of a range? If it is defined given depending on the kind of function that you are dealing with, then you will see what happens for that. But here we are saying f of t is 0 for t less than 0. Definitely this whole thing here will disappear. It will go to 0. Then you remain with the 0 to infinity, which is this one here. So change of scale is direct. Remember, this is a minus c to infinity. So if you wanted to take this minus c to infinity, then the change of scale would be obvious. We have already, when I say obvious, it means we have already looked at this. So if you have a u, and this u is a certain t minus c, we have already discussed this, then it is obvious here that your t is simply a u plus a c. This is u plus c, and that's why you see when you change, initially you had e to the minus st, but it is now e to the minus s instead of this t here. You now have a u plus c right there. Okay. And of course, now for the change of scale, remember your limits. Initially, you were, if you have u, your u in U, you are moving from minus t to infinity. So if you have this, then of course you know that your du is simply a dt. And if a dt, so that dt becomes a du there. And of course, if you throw in the limits, you have your limits. These things are, I'm sure you are also bored because we have already done this. Problem are the grammars. So if you are moving from 0 to infinity under t, that was this one here. We are moving from 0 to infinity. But now under u, remember if t is 0, then you will have your minus c here. And then, of course, this will still go to infinity. So that's why you have a minus c to infinity fu of that. And we know that under that condition there, this one here, it would be 0. So that one disappears, and then we remain with this other part. And that's why we end up with e to the minus sc, then that integral of that. And from this, we can now go back. And we say, if this is the case, then surely we know that our e to the minus sc, this one here, is that term there, is L f of t. But this f of t is simply the same as fs, because you see this is minus su. And from that, we deduce that this is the case, the case in blue here. Okay, that's the proof to that property to shift to the right. And of course, you can shift to the left. You need to understand this, because now when it comes to shifting to the left, it is just a change of sign. Where we have L, the Laplace of f of t minus c, this thing simply becomes a positive. That will be the only change. And then you go through the same integral properties and you come up with the derivations. So now that you have comprehended this, we can just quickly go through these very obvious examples that I can discuss one, you do the others really. So here we are basing our analysis or arguments in an attempt to get the solution to this derivation here, which derivation is linked to the theorem we have been using previously. So here, if you have a certain ft, remember we now have ft. So we have L f of t, we have this term here. If it is s over s squared plus 9, then can we find this one here? Then if you relate this with our proof in 1.5.4, the c is the 4 here. That's why we have e to the minus 4s. We've already been given ft, which is this. So the f of t minus 4 becomes that term there. So in simplicity, if you have a certain f of say t minus c, then the question is, can you extract the ft? Once you can get the ft and then you compute the Laplace of this, remember the Laplace of this will be the fs, then you get the fs, then it means once you have fs, you can now compute this one here, given that the derived formula, which is e minus scl of ft, the c will be derived from this term here. So it's quite direct. So in this case, you are given lt minus 1. So can we now associate this with our definition of ft minus c? There is no f here. That's why now from this, we extract ft, our ft. So our ft will be that t there. Then we know from the powers of t, this is basically a 1 over s squared. if you compute the Laplace of this, guys, then the Laplace of that t there. So that gives you this 1 over s squared, that term there. And now you had the t minus 1. If it was t minus 1, then from this we can get our f of t minus 1. But the minus 1 is the c there. So it implies that the L f t minus 1 is simply e minus sc. But remember, this is 1, which is just the e minus s. But the ft was t, which was 1 over squared, which is this whole thing here. And you are sorted there. Right. Okay. Of course, there are more examples here. You have sine t, you have sine t minus pi. I've told you once you have this, look for ft. So if you look at this one here, from this, if you're given this, then the question is, what is ft? Your ft will simply be the sine t. That will be sine t. Then the question is, if you compute the Laplace of this one here, which is the Laplace of sine t, this will give you the fs. And what is this? This is the, okay, it is already written here. I'm just repeating myself. I don't have to rewrite this. I had not focused on the right up down here. Okay, you have this. From this we get ft, which is that one there. I don't have to repeat myself. And then given this, you find the fs, which is this. We looked at the derivations of those trigonometrical functions that you already know, guys. And then from that, since we have this, we can now go back to this. So we know that from our definition, remember it is E minus SCL of FT. Is that okay? These are the box brackets here. So the C is the pi, that is the e to the minus pi s, then the fs, but remember we have already computed the fs of sine t. This one we already know, it is this one here. Then you just substitute it here and you come up with the answer, which is that one. Okay, we can now leave that one alone. We don't have to dwell much into that because everything is now obvious from the derivation. I insist that these statements must be at your fingertips, because once you're given a problem such as that, you only have to recall this simple fact here, and then you apply it and you quickly come to the solution. Right, you can go through all of these ones. We have already looked at these step functions. Nothing interesting, everything is boring. Shifting to the left, I've already told you this one was a minus. Same story here, you simply deal with the addition. It becomes t plus c. For the right, it was t less than 0, but now here our parameter is positive. That's why we say c greater or equal to 0. And then you deal with the shifting, but now here we are also saying for t less 0. So same story, you deal with the change of properties, and then you come up with this conclusion here, which I'm not going to repeat myself because I've already done this. And when you over repeat things, they say too much of anything is bad. So over repeating these proofs, it will overly bore us to even probably forgetting the most obvious. Okay, so that is that. There is nothing to really comment on this because we have already preempted this in the previous sections. You come and you have some examples there. Here you dealt with periodic functions. So same story here. We are saying if you shifted the pi units to the left, then of course you would lose the first half of the period. I told you we are borrowing heavily from little as 1. I've been sketching graphs since we started. So if you sketch, then you'll understand what we mean by losing that term, implying that sine of t plus pi is simply a minus sine t. So here, when you compute, given that this is the equivalence of that, so instead of looking at the Laplace of this whole thing, it is equivalent to looking at the Laplace of the minus sine t, which is right here. And then when you do the necessary and you substitute in this formula here, then you remain with this integral part here. And when you deal with this integral part, you realize that the whole of this is simply equivalent to that. That is the statement we are uttering here, that for the last part of the integral, or for the last integral, this is equal to that. That is if you deal with this and you substitute. So simplifying this, of course, here when we talk of the parameter, you must know that the key thing in this is that parameter C. Remember here in our general derivation, because this picks up from the other one, you still have a C. In this one, it was negative, it becomes positive. There is nothing to stress about this. Here we had it as a minus SC. In here, it is simply a positive. If you are looking at it in terms of the left shift, that one there. Okay. And even here, it is positive. So you can just factor out the E minus SC and remain with the LFT plus that one, rather minus, which is the direct application here. We have factored out that, and then you remain with this. Okay. Damping effect. Same story here. Here, when you talk of damping, we are just looking at that S there, and then we replace, we bring in some complex term here with the real and the imaginary parts, where A and B, we are calling them arbitrary constants. Of course, these constants can be defined depending on the actual problem or phenomena you're trying to unpack. Okay. So in this case, we are saying if you have, by definition, L of Ft is given by that, then it's just change, a replacement of S, and then you go into similar derivations for trigonometrical functions. So if you replace that S with S, this term here, or that term, remember, if you have this, there is what you call the complex conjugate. Okay, so which is now, it is plus minus. So this is the positive part of it, and then you have that one, because you always have two roots. You deal with this. This is from your complex analysis. There is nothing much here. These things you have already done. You come and you simplify this, you'll end up with the last term. Of course, if you take the imaginary part of that, if your B is 0, you end up with this statement here. And from this, we are saying the negative, of course, if you look at this function, just I can just call it a generic function, E, this could be to the plus minus. If I call this one lambda x, I am saying if I look at this in a more general sense. Okay, so this will either grow or decay, given that this is plus minus. For each negative, you expect a decay. How fast and how slow, if you could simply think of it in terms of shape parameter, that one will basically be based on this parameter lambda here. Is that okay? So Because of that, then the nature of the damping, because damping here can be categorized. It could be fast, it could be slow. Even for some of you who do physics, there are these people always complaining that physics clashes. When they talk of damping effects, then for you to understand a damp, definitely you have to bring in simple harmonic motion. And once you bring in a simple harmonic motion, then the question is it fast? Is it slow? It depends again on the process you are looking at. For cars, you expect them to damp very fast, those critical damps, because if it becomes slow and it behaves, these guys of physics who have done fluid dynamics, if it is overly slow in the form of a viscous drag, then of course that car can easily cause accidents. So when we talk of the damping rule, this so-called damping rule is embedded in that exponential term. That's why we say that the negative exponential damps the function ft, hence the name damping rule. Even if we remove this one and we say damping, it is the same. Then the question is, if the damp goes to 0, what would that imply? So when you unpack this in an attempt to simplify it, we are saying that if b goes to 0, you'll get that, but you have the e to the minus 80. Here it is minus 80. I've generalized it with a plus minus for the plus to cater for a growth, because when you talk of damping, you may have some kind of motion like this, but these amplitudes may be different. This here may be different from the next amplitude, and the next one may be less than the previous one. So the variations in these amplitudes here are all catered for in here, and those will depend on the value or how lambda varies. These guys who are into physics, I'm sure they have dug deep into this, but you don't have to be specializing or taking courses in physics to understand this. Even those who did some physics in O level, rather A level, you should be able to comprehend this. Right. From that, we can go ahead and from this, after getting to do the substitutions, you come up with this. Now, of course, the Laplace of ft cos of bt, Laplace of ft sin bt. This one we have already finished. We did this. We did these derivations. These ones we have already done. So the output will depend on the nature of these ft's. Is that okay? So is ft. If ft is t, so you have a certain t with the cos bt, then you know here you have towers of t. Is it something related to a gamma function here? We have already discussed the gammas. So ft is the key determinant of the nature of the solution that one is going to get. Otherwise, for cos bt and sin bt, we already looked at these derivations. Right. Everything today seems very direct. Determine the Laplace transform of okay. Now here there is a t cos bt. This is what I think I was indirectly mentioning here. So for t, that is the powers of t, you can get that one now, t cos bt. Guys, we have already looked at these derivations, so just substitute. And once you substitute, you have the answers. Exponential shifting rule. Be mindful that this session will run out in the next 3.5 minutes. As soon as it runs out, guys, just log back in using the same link As soon as it runs out, please log back very fast into the session. The lecture is ending at 11, so don't take long to log back, to log in into the next session using the same link. Okay, there is nothing for me to discuss here, really. These things we have already looked at them. Same story, exponential shift. My explanation is not different from what I have just explained. You have a function, so this is EAT. This is for your growth, and this is for a decay. Remember, I've just generalized this. And by the way, these are key for people who do anthropology, or some of you who may be taking interest in working with these NGOs. You know, there is too much in terms of moral decay these days. And for you, if you specialize into mathematics, and you can actually scoop yourself a fat job, and you work with anthropologists. Anthropologists, these are people who study behavioral dynamics, and these functions are also key. If you look at the way people usually behave, people tend to behave better when there is fear. And when there is no fear, people tend to behave recklessly. And in terms of that, if you just run a very quick demonstration, why I'm bringing that in, when you talk of this exponential shift rule, and it is covering both, the plus minus is covered here, then you can just look at, I can cite a very simple scenario here. Is my writer. Okay, there we go. So if you look at this here, and you can just look at a few scenarios. I can generalize something that most of you probably are common with. So if this is time t, I can go up to, this is 2021. So if I put 21 here, it means that's 2021. And what is this? I can call this one, I can generalize this. Let's look at a disease like, say, HIV. I think some of you guys, these things have been preempted already in biomathematics. I don't know who is handling you in biomath. Maybe it's Dr. Nanyonga, Betty Nanyonga, or could it be Dr. Hassadi Dumba? Whoever is handling you in that, somewhere they'll have to cite some of these, because here, if you look at, let me call this one incidence I can just call this I, or stroke P. P for prevalence. Prevalence with respect to diseases like maybe HIV, most of you are likely to be commonly